Let's consider a particle that's moving along a straight line and has velocity given by the function t squared minus 3t minus 4, where t is the time in this problem. We can see a graph of this function, and we'll see that if we can consider both displacement and total distance traveled on the interval 2 to 6, that the particle begins by moving, or is initially moving, I should probably say, in the left. If we think of this line as going from left to right, at some point its velocity hits 0 and then it begins to move to the right. And we can see that by the fact that the function is initially underneath the x-axis, saying that we have negative velocity values, and I'm interpreting that as motion to the left. And then we're going to cross through a 0 or an x-intercept. We're going to start getting positive velocity values, and again, I'm interpreting that as motion to the right. Our velocity is changed in its direction. So by the net change theorem, the integral of this function on the interval from 2 to 6 is going to give us the displacement. So let's consider the integral from 2 to 6 of t squared minus 3t minus 4 dt. That is going to be 1/3 t to the third minus 3/2 t squared minus 4t evaluated from 2 to 6. So that is going to give us 1/3 times 6 cubed minus 3/2 times 6 squared minus 4 times 6 minus, we're going to have 1/3 times 2 cubed minus 3/2 times 2 squared minus 4 times 2. And let's see what we get if we do that. So let me pull out my calculator here and see what I get from doing that process there. So I'm going to have 1/3 times 6 to the third minus 3/2 times 6 to the second minus 4 times 6. And if I've typed that in correctly, I get negative 6 there. Then I'm going to subtract from the other piece here. We're going to have 1/3 2 to the third minus 3/2 2 to the second minus 4 times 2. And I get a negative 34/3 when I do that. So if we take negative 6 and subtract a negative 34/3, let's see what we get. I get 16/3. That's the displacement. That is the distance that the particle is from its position at time 2, 2 times 6. So if we figured out what its position was at time 2, took a snapshot, looked at its position at time 6, took a snapshot, and measured the distance between those 2 points, we would get 16/3. Now that isn't the distance that the particle actually travels, because it's moving to the left initially, and then it comes back and retraces its route and moves to the right. So any of that area, or any of that route essentially that's being retraced, doesn't show up in displacement. Displacement is just looking at what happens at each of the 2 endpoints and at nothing in between. To determine the total distance traveled, we're going to need to take a look at the different intervals on which the function is both negative and positive. So if we look at the first interval here, from 2 to, and this will turn out to be 4, if you look for the zeros of the velocity function, you'll find out the velocity is 0 when t is -1 and when t is 4. We're only interested in 4 because that's the only value in this interval. We can see that the area, or the displacement if you will, is negative in the beginning all the way up to 4, and then it becomes positive. What we'd like to be able to do is make that negative area positive. So let's consider the following. Let's consider the opposite of the integral from 2 to 6, or excuse me, 2 to 4, since that's the interval on which our function is negative, of t squared minus 3t minus 4. If we take the opposite of the negative area, that'll make that area positive. And then we can add on the positive area, which is from 4 to 6 of t squared minus 3t minus 4 dt. So here's the general idea for getting to total distance. We need to find the zeros of the function, in this case the zeros of the velocity function, they're x-intercepts. We're going to use those to break our integral up into smaller intervals. On some of those intervals, the integral will be only negative. On other intervals, the integral will be only positive. On the intervals, where the integral is only negative, we're going to reverse the sign to make them positive. And if we do that, we'll end up with our total distance that the particle travels. So let's see what we get if we do this. All right, fixing a couple of things here. We're using the antiderivative we saw before. We're going to consider 1/3 t to the third minus 3/2 t squared minus 4t. And we're interested in that from 2 to 4. And we're going to want the opposite of whatever we get from that. And then we're going to add. We're going to be interested in 1/3 t to the third minus 3/2 t squared minus 4t. And we're going to want to do that from 4 to 6. So let's see what we get here. I'm going to work on the first part to begin with. And I'm going to start with 1/3 of 4 to the third minus 3/2 of 4 to the second minus 4 times 4. Make sure I've typed that in correctly. That looks good. So I'm going to get the opposite of a negative 56/3 minus, we're going to have 1/3 times 2 to the third. And we've already done this part previously, so I don't actually need to retype this into the calculator. We got negative 34/3, so we're going to subtract a negative 34/3 here. And then to that we're going to add, well, we're going to plug 6 in. We've already done that once before. So we're going to get negative 6. We're going to subtract whatever we get at 4. Well, we just did 4, and we saw that we got negative 56/3. So we're going to subtract a negative 56/3 here. So let's see what this gives us. We're going to get the opposite of, in parentheses, negative 56/3. I'm going to write that as plus 34/3. That would obviously come out negative originally, and that's what we expect, but we're going to take the opposite out front of what we have inside the big parentheses there, so that's going to end up being positive. That's good. That's what we want. To that, we're going to add negative 6 plus 56/3. And let's see what that gives me. I get a total displacement of 20 units, whatever units it is that we happen to be talking about in this case. So quite a difference in these two values here.